Today we're looking at Elusive's failed DC-DC converter out of the Honda Insight. And I have fixed this, but I wanted to go into details about what I'm seeing here because I think we're going to start seeing this issue more and more due to electrolytic capacitor aging. I've said for years that I've never seen one of these fail, and now within a week or two of each other, we've had two of them fail with the same issue, or at least the same root cause. I don't know what the actual failure point was. So I'm going to hook up a couple signals here just to show those in a second. I will explain them later. So if we look at the actual defect, or the actual failure mode here was there's a 2.2 ohm fuse here. And if you look at EEPROM's excellent schematic that he created last year, the failing part is on page 2, and I've highlighted it in orange. I know you're not going to be able to see this, but if you look on page 2 in the schematic, it's basically you have the HVDC positive here, and then this positive comes over here and runs through this 2.2 ohm fuse. This is basically running like kind of a bootstrap circuit. It just generates a 12 volt rail or a 13 volt rail. It's not the 12 volts that you get on the output here. It's the 12 volts that controls the isolated logic on here. So this supply has at least 3 different 12 volts that it uses. It has this 12 volt out that it's generating. It has a 12 volt in that's coming in through the wire harness. And then it has this local 12 volts that's generated from the HVDC bus before any of this logic is even energized. So this specific circuit here is just using a kind of a flyback transformer to just generate, it's using this top 200, which is a discontinued part. That's basically a 100 kilohertz oscillator with a built-in MOSFET with a drain and a source, for example. And so this is basically, this is just turning on and off 100,000 times per second, essentially, and it can push some current. It's a 700 volt rated part, so it's a tank. The failure we had, again, was in this 2.2 ohm resistor. And so I fixed the failure before I did any more analysis, and there were burn marks. You could actually see on the lid, it was pretty obvious where the failure had occurred. This 2.2 ohm resistor just stopped existing very, very quickly, and we'll look into see why it is that happened. It didn't overheat. It over existed, and then it just stopped existing. So how does that work? I want to show this here, which is the drain and source of this top 200 part. This is what we'll be focusing on as we take this apart. I wanted to show you the behavior before I take it apart so I don't have to put it back together again later and show you. But basically what we have is between the drain and the source here, we have the full pack HVDC positive, and this car that this was coming out of had the IMA bypass installed for a while, which means that the HVDC rail was basically proportional to the engine RPM, and it could go up to 220 volts, at which point it would disable about 217 volts. But it could go up to 240 or wherever it would go to because there was no battery. And so this circuit here, again, was being powered by the HVDC. This is the HVDC positive, this is the HVDC negative. And so this circuit was whatever that HVDC bus voltage was. There was no battery stabilizing it. And eventually, that doesn't really matter, the fact that it was varying, but the fact that it was able to get really high caused the failure that occurred, which is again leaking electrolytic capacitors, specifically C204. We'll look at it here in a sec. It caused the electrolyte that had leaked out, which is conductive, to basically catch on fire and start a plasma arc that, we'll see, it's interesting. So yeah, let me show you this here. We're going to be looking across the drain and source. So this is going to be showing you the HVDC bus voltage on the switcher here. So this is again a 100 kilohertz switching supply. So I'm going to turn on an external supply to 90 volts or whatever, and you can see immediately that we have voltage here, and I hope this is kind of legible. Yeah, you can totally see that. So this is our switcher here, and so we're at 25 volts per division. So right now we're averaging 86 volts. We're about 25, 50, sorry, this is 50, 100, 150 volts here, even though we're only applying 88 volts. I haven't even applied any 12 volts to this yet. If you can see the display here, this is 0 volts. This is the 12 volt battery or whatever. This is actually a programmable load. I've got an external supply for that. But you notice this works even without the 12 volts. Whenever high voltage is applied, this circuit works. There is no control logic on this circuit. Again, this is generating the 12 volt rail that is then controlling it. So this V plus here, which is 13 volts or whatever, all the purple signals you see, all these logic highlighted signals, there's none on page 3 or 4, I don't believe. But on page 1, and again, I know you can't see this schematic, but you can pull up EEPROM's schematic here. But basically you can see all these purple things, all of the internal op amps and stuff that are controlling like what the output voltage is and whether or not the supply is enabled, they're generated by the HVDC bus's 12 volt rail, which EEPROM is just called V+. I would call it like HVDC 12 volts or something. That's not a good name either, but something. You can come up with a name. V+ works too, whatever. You get to call it whatever you want. You make the schematic, you call it what you want. So this circuit is now running, and if I actually connect my 12 volt battery, let me pop this off. So here you can see 11.08 volts. You might not be able to read that, I'll read it to you. And so this is basically, we're in a state where the key is off, and so now I'm going to turn the key on, and this rises up to 14 volts. We now have our HVDC. Now one thing I want to show you though is that we have 150 volts here now, but you can see that as I ramp the HVDC voltage, this just ramps right along with it. So this is 160, 170, 180, 190, that's 200 volts right there. You can see we now have 50, 100, 150, 200. We have 250 volts there. You can see that our circuit is doing some fun things here in analog land. I'm not going to explain those, but this ringing, by the way, is real. I thought initially it was in my leads. It's not in my leads. This is actually in the signal here because we have some long inductive traces on the circuit board. So anyway, you can see that this is working now. I can actually come out here and put a programmed load on here. I'm going to put a 10 amp load on this, and you can see we have no problem generating. Actually, we do have a problem because I have a current limit on this supply right now. Let me try again. So I'm using current controlled, current limited supplies here, and that was basically catching what it thought was a safety condition. But you can see now here, I'm doing 10 amps at 13 volts, no problem, all day long, we can run it. So this supply is working now. This will only test to 15 amps, but I have a 30 amp and whatnot. But I'm certain this supply works. I would, of course, test it more if I were shipping it out to a customer. So now we're gonna take this apart, and I wanna show you the public service announcement, the thing I'm actually concerned about here. So I'm just making sure the voltage here is 0, since I did have high voltage there. Oh, look at that, my lead broke right after I used it. In fact, we don't know that we measured that. So let's put our positive there. Yeah, it's still 0. But anyway, I did just break that lead. That happens from time to time. Those get a lot of use. Okay, so again, here's the part that failed, this R145. I didn't have a replacement 2.2 ohm, but I had a 6.8 ohm, and I just put 3 of them in parallel there. This is a very low current circuit here. This is only this supply is only rated for like 400 milliamps output or whatever. This 12 volt rail again is not the main 12 volts. This is the auxiliary 12 volts that supports all of the electronics on here. So this piece basically got obliterated in a fireball, and I want to show you why that happened. I need to remove some screws. I've already removed all the mechanical support screws, but here I'm just going to remove the electrical screws that are doing, this is our HVDC bus, and this is our 12 volt output after we come off the magnetics there. Different 12 volt rail. This is the actual 12 volt rail that charges your 12 volt battery. So we pull that off. There were more screws. Again, I've already removed them, and then we need to disconnect these connectors here. So this is, again, the input resistance for this switcher here. I'm a bit bummed that TDK didn't put a fuse here for this circuit, because all of these traces can't handle the HVDC that would pop 30 amps. You know, the fuse that's on the junction board, these small traces can't handle it. So I would have really liked to see, you have seen a 2 amp fuse here, because again, the max is going to be like 500 milliamps or whatever. But they don't have it, and because of that, it actually obliterated some traces. We can actually look here, and you can see that here's my fix, and I'll just use the camera rather than my ocular. You can see I just did 3 of these 6Ks in parallel here. These are the same nets, but like this trace burned back quite a bit. I had to go several millimeters to go back and find it. And that just shows you how quickly this happened. If this were an overheat failure, the copper traces aren't going to melt. It's going to be the part that melts. And in fact, I do have the original part here. Let me set this on that or something. Here's that 2.2 ohm resistor that was there. And you can see that it just absolutely cooked. Get that error flag off of it. Oops. Okay, so there is our original 2.2 ohms. I gotta go higher. Okay, there we go. So you can see this 2.2 ohms, and this auto exposure is just terrible. Let's see. There we go. Okay, so here is our 2.2 ohm resistor, and you can see it's basically open because it just totally burned everything. This failure happened in a matter of tens of milliseconds. So that guy got totally obliterated. If we look, I'm gonna make sure I keep this guy here, capture him with the flag. Oops, there we go. So here's where we were drawing. Okay, well now the exposure is bad. So here's where we draw the actual HVDC in. We go through a diode and this resistor, and then we have a capacitor there. Notice I only replaced this one part. Nothing else is actually broken, but put a big asterisk there because there are parts that have failed. We're gonna look at them next. They've failed, but not in ways where they're immediately unstable. So this is our top 200 switcher that I was talking about. We were measuring the signals on the back of this guy. So top 200, discontinued part, but again, it's just a 100 kilohertz switcher, and it'll switch, 400 milliamps or something, just enough to generate the logic where you can then make your big 12 volt rail that you need, because you need control signals because you have feedback and whatnot that you need to get in there. This part's actually totally fine, although if you look here, you can see that we actually had a plasma arc across here that burned. This is actually pretty cool. If you ever played around with like a Jacob's ladder as a kid or as an adult, I actually made a Jacob's ladder for like 6th grade and brought it to science fair, and they wouldn't let me plug it in. I was really upset about that. But if you look here, you can see that this capacitor here leaked, C204, and C204 is just coincidentally, it's the same circuit as this R145. It just happened to be location-wise in the same spot, which makes sense. It's a filter capacitor or whatever for electrolytic. I would really like to see a ceramic capacitor in front of this electrolytic. Electrolytics, they don't like current spikes. It can cause them to fail. This is a steady DC voltage. Even though it goes through this current phase here, this is actually just a start winding, just to kick something off. But once that's gone through, this winding just saturates here, and there's no switching that's happening through that. It's just a first pulse there. I'm sure there's a reason for that. I haven't really looked into it, but it's basically doing the control input here, which is our logic input. This is just a 5 volt DC signal that we're generating off of our high voltage. So it's not an isolated, it's not a safe 5 volts, but it's 5 volts nonetheless. And yeah, so what has happened here is the C204, this electrolytic capacitor here, has leaked, and you can see this leakage on the circuit board. So I don't know if this is going to be gigantic yet. So all of this material here is actually electrolyte that is leaked out. And you can actually see it's leaked out under this glue. These are of course glued in place because they're 2-terminal devices and they don't want them to vibrate off. This one is leaked really, really, really bad, and this is the one that actually caused the failure. Enough electrolytic juice fell out of here and went between these 2 pins. These are the 2 pins we just measured where we were seeing 250 volts on our switcher with a 200 volt input. And what happened is this conductive electrolyte eventually leaked out here and got between this very small distance. And when that happened, it formed a plasma here, and this plasma actually traveled up these contacts on this TO case and came all the way up here. This capacitor in the car, I mean, this is the top. So the arrow is pointing towards the top, and a plasma in air will travel upwards along conductors, particularly when they're in parallel like this, again, like a Jacob's ladder. And this plasma just stayed here and just arced until it opened. And what opened? That was the 2.2 ohm fuse that we replaced on the back. So all of these electronics are still working. This capacitor has much less capacitance, but even though it's leaked all this electrolyte, it is still working. We just saw that the circuit was working. But this failure here caused a low resistance, very, very high current, because again, this is an unfused HVDC. The only fuse is the 30 amp fuse on the junction board, which is 30 amps at 200 volts or whatever, you can push 6 kilowatts. Yeah, that sounds a lot. And so that's basically what happened here. We had this plasma arc here, and you can just see where it pitted it out. And in fact, this case I've cleaned off because I needed to make sure it wasn't the case where the die of the case had shot out the side. I needed to make sure of that. And so I basically kind of looked in here on the side and cleaned it out. And I know that's kind of dark now. Let me again get this exposure up. I wish the auto exposure worked better on this app. So the burn marks you see in here did not come from inside of this die. Again, it's just the plasma, and you can see all of the electrolyte that was on here. And you can see here where we burned this pad. When this short occurred here, this short obliterated the copper here. And so the electrolytic also obliterated, and it's what formed this plasma material, right? We basically turned the solid electrolyte or the liquid electrolyte, depending on what state it was in, into this plasma that then just traveled up here, there, and then just burned until it petered out. And you actually see it pitted the, this is either the, I don't know if this is the source or the drain or the collector. I don't remember the nomenclature they used on this, but this is one of the 2 high current pins, and you can see we just kind of ate through it here. So this capacitor leaked. This capacitor is the root cause, and you can see again here where it, the electrolyte has also dissolved this copper partially, but not all the way through. It is still working, it is still conductive, I had checked that earlier. But you can just see this is space junk, where we still have copper underneath, but this electrolyte has started to eat through it. But you can see that we do still have copper the whole way through. So we are still making a connection there. And you can see some other surface attack here as well. And oh no, we see something over here. We'll get to that in a minute. This is more electrolyte that has leaked out. This is an attack on this surface where the solder mask has failed. This DCDC board does not have conformal coating over all of its traces. So the environmental nature is only prevented by the, the solder mask, the green that you see here. That's just this very thin layer covering the copper, which you can see here that the electrolytic inside of here turned into dirt, essentially. Hasn't fully attacked that copper yet, which is good. That's one of the reasons this supply is still working. But we do have 2 other failing capacitors as well. So here's one of them, and this is the one that someone else had posted on. So this again is Elusive's DCDC, but someone else posted, I believe, this exact same capacitor was leaking. And so what I found looking at these boards is that the 3 small capacitors on here are all leaking. So here's the second one. This is C303, which is some completely unrelated circuit. I found it on here, but again, it doesn't really matter where it is. It has just failed. So here's the one of them. That's the next one we'll look at, C551. It's actually, this is so weird. They're using an electrolytic 22 microfarad cap as an integrator on this op amp, but it's electrolytic. Man, you really should be using a ceramic or really COG, but of course a C0G at 22 microfarads would be crazy large. You'd probably want to have a cascade there. But yeah, using electrolytics on your inputs on op amps is not really a good idea. I love this supply. It's really well designed, but that just seemed kind of weird to me. And of course the missing fuse on this control rail, this thing where the terminals just made a fireball inside of here, a 2 amp fuse would have fully contained that, and then you could have gone in and seen before it burned all the traces off. You could have seen what the issue was. I'm looking for that one cap. Oh, 303. So it's just the 5-volt regulator. So there's some 5-volt logic on here as well, and it's just it's probably just an LDO. I haven't actually found that. It doesn't really matter. But yeah, C303 is the one we're looking at right now, and then 551 or whatever. This is the other one here. It's also leaking. This here is damage I did trying to remove this so I could read the label. Yeah, C551. But all three of these capacitors need to be replaced. And the problem is that, you know, these are 25 years old, up to 25 years old now. In fact, they're probably all 25 years old. You know, TDK probably made these once, maybe twice. I bet they didn't make these after like 2003. Although they did have a service bulletin where they had to recall because one of the onboard temperature sensors, I believe one of these was breaking or was not connected properly. It wasn't measuring the temperature correctly. So there was a service bulletin where they had to fix these. But yeah, I'm sure they weren't making these in 2004, 5, or 6. The point is these are 20 plus years old at this point, and electrolytics just, they have a lifetime. They're a wet electrolyte on the inside, and once those cans start leaking and they leak out, you know, sure, it would be nice if the electrolytics inside weren't conductive, but then of course they wouldn't use them in capacitors. But anyway, yeah, so that's the PSA, is that these are getting really old, and I'm gonna make a recommendation. There will be a follow-up video that will be just, you know, how do you fix this? It won't be as technical, but I'm gonna recommend that we replace all of these aging electrolytics. I've only seen the smaller three, which are 22 microfarad, 25 volts. And then this one here is, the first one, the one that actually failed, is a 47 microfarad, 16 volt. And that's on the 5 volt rail. And then these are on also 5 volt rails, but they're different voltages. So kind of weird, but yeah, I'm gonna recommend, and I'll probably make a kit. I am not gonna offer a repair service of my own. I just don't have time to do that. But if someone else wanted to, I think that'd be great to have a, hey, you send me your DCDC that's working, I'll recap it for you, send you another one, that way you don't have any downtime. But I can't commit to something like that. I don't have the time for that, unfortunately. But I will post the part numbers for all these caps. And so these are you know, film caps. These are never gonna fail as long as you treat them right. But these electrolytics are, you know, they age, and once they age out, they're gonna die. So I'm gonna propose that we replace 1, 2, 3, 4, well, I'll just pull it out because you can't see under there anyway. I'm gonna propose that we replace 1, 2, 3, 4, 5, 6, 7, 8, 9 electrolytic capacitors. But that's it. There's no more electrolytics on here. I haven't really looked at this, but yeah, these are all film caps here, film, 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 film. And again, those are never gonna fail over time. So it's really just the 9 electrolytics here. And the reason I want to do that proactively is that, you know, right now these DCDCs have been in a state where forever and ever and ever I've said they just don't fail. And so because of that, they're not worth anything. But I think we're kind of sitting on a precipice here where these electrolytics are going to fail. The failure mode could damage, for example, this top 200 part, which has been discontinued for years. So you break this part, you know, that you could recreate something that would go in there, but I doubt there's a drop-in that would just work. Maybe there is, I haven't looked into it, but, and then of course it's blowing up the traces too. In this case, we only blew up, you know, the trace right here. I know that's not in focus, nor do I think I can get it, yeah. So this is, again, the R145 that we blew up that I've fixed here, and it is working now. Anyway, yeah, I would almost as soon just replace this with a fuse in series, you know, just dead bug it onto here, get a 2.2 ohm resistor, and then, you know, solder it in series with a fuse there, just so 20 years after you recap it, it just blows the fuse out. But, you know, that's a pretty proactive measure there. Just replacing these caps is certainly good enough. It'll give you another 20 years, and, you know, kick the can down the road 20 more years. Some of these, it's possible, the technology in caps might have gotten to where you could just put, you know, ceramics here for some of these. Like, yeah, you could totally get a 22 microfarad, 25 volt ceramic. But of course it's through hole and you'd have to somehow surface mount it. You could totally do it, and that would be more future proof. But again, I don't think you need to change anything. These have lasted 20, 25 years. So recapping these will give you another 20, 25 years at least. And by then there will probably be a lot fewer of these on the road, would be my guess. But yeah, just all the attacking here on these traces and whatnot. Of course, you can always fix this. These circuit boards are so low density, you could literally just run a wire wherever you needed to get to. But I do think to be a little proactive, particularly because you don't want to kill this part. This seems to be the place where the high voltage is going to fail. We've got a leakage point here with high voltage across 2 pins. And at some point, here's where I pointed out earlier that this was in a car that had the IMA bypass installed. So the voltage across these 2 pins at idle might have been 60 volts, and then you rev it up to 5,000 RPM, and maybe now it's 250 volts, 260 volts, 270 volts, you know, whatever. The DC-DC has shut down because the logic shuts down at 217 volts. But this is unadulterated HVDC, right? So you can't turn this off. The only way you can turn this off is to literally open the main contactor, but the MCM has no idea that any of this is happening. There's no logic there to even detect that. There's no way the DC-DC could tell the MCM, hey, open the contactor, the voltage is too high, or you know, whatever. So anyway, yeah, this is just these signals are space junk, leaks out of here, it deposits on the surface, and then you hit high RPMs at some point, and that's just enough voltage for this to conduct. Once this starts conducting, it makes a plasma, and that plasma becomes basically a 0 ohm short for as long as it sustains, which, you know, this probably burned for a few hundred milliseconds, did all of this damage. If you've looked at a plasma cutter, like, yeah, plasma cuts, and you can see again that as this spark sat here and dwelled before our 2.2 ohm resistor opened, we just kind of pitted the hell out of this here. We burned the trace off there, we burned the trace on the other side. This was electrolytically attacked here. But yeah, so that's the failure, and it's so similar to the picture that, again, the other forum poster whose name is escaping me posted, where this guy here, I believe, was failing. So my recommendation is going to be that we replace all 9 of these capacitors, certainly these 3 small ones, but while you're in there, you might as well do all 9 of them. They're all the same age, you know, like. So anyway, there will be a follow-up video that is not technical at all, and it's just how do you replace these things. If you know how to solder already, you're not going to need to watch that video, but you do want to make sure at least that you glue these new caps on, and again, that'll be in the video, because if you don't glue them on, then they're going to vibrate off over time because they're only a 2-terminal and they're heavy and whatnot. So anyway, yeah, that is this public service announcement about the DC-DC electrolytic capacitors aging. As far as the rest of the car, there are of course electrolytics elsewhere in the car as well. The HVDC bus inside of the PDU, which is the thing on the left in the IMA bay, has 3 of these guys here, these giant chunkers here. These are electrolytic here. And so those will eventually become an issue as well. And then, you know, every computer in this car, I mean, the IGBT pre-driver has probably a dozen, probably more than a dozen electrolytics in it as well. But this just happens to be the combination here of leaky electrolytic right next to very high voltage that's unfused, no current limit, and so that's what caused this unit to fail. And you know, I would think that as these electrolytics keep failing, because all electrolytics do eventually fail, they leak somehow, and when they leak, they just keep leaking, especially when they get hot. And the DC-DC definitely gets hot in here, so. This is a pain point that we are probably going to start seeing more and more as time goes on. And hopefully we can keep enough of these DC-DC converters alive, long run, you know, 10, 20 years from now, that we can still drive the cars with the original DC-DC. And if at any point we get to where we can't, then of course we could just use a different DC-DC, but you know, there's plenty of types of that. So that is this failure, which, you know, I've finally seen a failure on the DC-DC, and now I believe I've seen 2, you know, online. I've seen a second one which seems functionally identical. I wouldn't be surprised if that same resistor blew up as the current limiting device, since there was none. Yeah, this 2.2 ohm here. Yeah, this spark here, this is at 240 volts or whatever to start this ignition here. This is all goo from the 2.2 ohm resistor. This is probably pushing 3 kilowatts would be my guess, for maybe 4 kilowatts. And so across the 2.2 ohm resistor, I don't really ever do math in my head, but it's funny when you can, you know, conceive where, you know, what the wattage was, but you don't know the basic math. So we'll say, what am I even trying to do here? Let's say 250 over X. That's not right. Man, let's see. So that would be current. Man, I'm just gonna do 4,000. 16. It seems higher than 16 amps. But yeah, so if we did 16 squared times 2.2, yeah, it's definitely higher than that. So let's say it was 25 amps. Sorry, I can't math right now. That's not right. E to the 33. Yeah, it was probably closer to 30 or 40 amps. And again, a 30, or I haven't said it this time. I would say it's probably somewhere closer to 40 to 50 amps to get the amount of energy we would need to cause this much damage that quickly. 50 amps is not going to blow out a 30 amp fuse, especially the fuse used on the junction board for the DCDC. That'll handle 50 amps for, you know, seconds or whatever. And this whole event happened in like tens to maybe 100 milliseconds. Just looking by this blast radius here, you actually see that this, as this came off, it actually damaged this cover here. So this is not a slow burning thing. This is a very, very fast, high energy failure across that 2.2 ohm resistor. And again, I would just love to see a fuse in there. I love this DC-DC converter. I've always speaked praises of it. It's one of the most beautiful laid out power electronic devices I've ever looked at. Just as far as its elegance, its beauty, or whatever. Most people probably don't get the same satisfaction out of it, but I just love how they pass the high voltage to this board and then they pass the low voltage back over these magnetics. It's just really well done, and it's what you would expect from TDK Lambda, but you can't get everything right all of the time. I have definitely shipped products in the past that didn't have fuses in places where they needed them, and I actually had one burn down once where like 4 inches of the customer's PCB burned down because there was this high current, you know, a 10 amp sustained short through a poly fuse that was self-resetting, and we were able to reproduce it in our lab exactly as it happened with the customer. So in like a fume hood, we were able to reproduce the exact failure, like down to the millimeter where it burned. And of course the solution was we added a fuse. But yeah, it's really difficult. Sometimes you miss stuff like that when you have like a 30 amp bus bar here. This is 30 amp fused, but then you pull a small amount of power off and you forget to fuse that element. Anyway, yeah, that's it. You know, one more thing to watch out for on these DC-DCs. I'm going to probably start harping the proactive replacement. So whenever you're in the IMA bay, pulling the DC-DC off, recapping this thing, just because you don't want this to fail. In this case, we lucked out and we were able to fix it. But if this plasma had stayed for a while, it could have burned the traces, could have killed this part, this non-replaceable part, because again, it's EOL. So I'm going to do it in my car next time in the IMA bay. This is not something like you do tonight, tomorrow, but you know, when you're in the IMA bay, I'm going to say probably you're going to want to recap. And I'm going to buy a bunch of these capacitors so that I can send a kit out for, you know, like 10 bucks or whatever. You know, not in it for the money, but you know, I'll send the 9 caps out and I'll just put the parts down if you just want to do them yourself. You want to buy them on DigiKey or whatever. Yeah, so as always, thanks for watching, and another thing to worry about, but it's not going to keep me up at night.